So in the last few lectures, we have talked about chemical reactions. And we've given a lot of detailed information about how chemical reactions work. But if we think about how they are used in communication systems and molecular communication systems, it helps to think back to the block diagram model of a communication system. So we have our transmitter, channel, and our receiver. How are chemical reactions used? So we talked a little bit about this. At the transmitter, the chemical reactions can be used to produce molecules that are that can then be released. In other words, it produces the signal-bearing molecules, and it can be involved in the process of releasing those molecules. At the receiver, chemical reactions can be used to pull the signal-bearing molecules out of the environment and can do things like taking action based on whatever signal was received. In the channel, chemical reactions are not so important. I'm not going to say that they are unimportant, but they're not the most important physical phenomenon happening in the channel. So we have reactions here. Reactions here. What's going on in the channel? So in the channel, we have molecules released from the transmitter, and they're supposed to propagate to the receiver. If we think about traditional wireless communications, from the transmitter to the receiver, we have electromagnetic waves propagating in free space. But now, and we know that we know the physical phenomenon by which those electromagnetic waves propagate. It's given by the wave equation and Maxwell's equations. But in this instance, we are releasing particles, we're releasing molecules from the transmitter. And those molecules are supposed to propagate through this environment to the receiver. Now, in any gaseous or liquid environment, the method of propagation of a molecule from one point to another is by a process called diffusion. So in this lecture and the next lecture, we're going to talk about the physics of diffusion. What we're going to see is that diffusion has a huge impact on molecular communication systems. It's again, aside from reactions, it's the most important thing to model and to understand. And it will contribute significantly to the noise processes, particularly because it is a process in the channel. We're going to look at two kinds of diffusion. One is, I'm going to call it microscale diffusion. And by that, I mean diffusion where individual molecules are significant. So in other words, if you're looking at a system where the scale of the system is such that individual molecules can be resolved and are important as far as modeling the system, then we're going to call that microscale diffusion. And at this scale, what we talk about is Brownian motion. And mathematically, we call it the Wiener process. Alternatively, what I'm going to call macro scale diffusion. In this instance, individual molecules can't be resolved. And at that scale, what we're talking about is things like the diffusion equation sorry, actually, the diffusion equation, there's a better term for it, it's called Fick's law. And the quantity that we're dealing with is concentration. So up here in microscale, what's going on is we're looking at the trajectories of individual molecules. At macro scale, we're looking at, in the aggregate, the concentration of molecules, and they're propagating by Fick's law. So what we're going to do over the next 2 lectures, this lecture, we're going to talk mostly about microscale diffusion, and in the next lecture, we're going to talk mostly about macro scale diffusion. So in microscale diffusion, the trajectories of individual molecules can be resolved. So what I'm going to do, most of my examples will have to do with one-dimensional diffusion, but they're easily generalizable to multi-dimensional diffusion. What I'm going to do is I'm going to define the particle that has a position at each time. So my time variable is going to be t, and the position, I'm going to call this b of t. B here refers to the fact that it's a Brownian motion. B of t, if B of t is a Brownian motion, then physically it is governed by random collisions with other molecules in the environment. So this is where Brownian motion comes from. A scientist named Brown observed, I think it was pollen through a microscope, and basically what he saw was that the pollen particle basically did this. It jumped around. So he couldn't see this, but I'm not sure if it was him or if it was someone later who deduced that the reason for these jumps, these random motions, was that water molecules, which he could not see with his microscope, were constantly hitting this particle in a random way and causing it to jump from side to side, meant to do a random walk. We model Brownian motion, B of t, as a Wiener process. So B of t is a random process. Its model is given by the Wiener process. The Wiener process has two criteria. So B of t has 2 properties. First, for times T1 and T2, the increment in B from T1 to T2, which I'm going to call this B of T2 minus B of T1, This is a random variable. I mean, each of these positions is random at T2 and T1. The difference between them is going to be a Gaussian random variable. So n means this is the Gaussian distribution with mean 0 and some variance sigma squared times T2 minus T1. So notice that variance is proportional to the difference in time. With the constant proportionality being sigma squared. We'll talk a little bit about sigma squared in a minute. It has a nice physical meaning, but we'll just leave that for now. Second property of a Brownian motion described by the Wiener process is that for disjoint intervals, the increments are independent. So if you imagine a timeline and you have two disjoint intervals, let's call them T1, T2, T1 prime, T2 prime. The Brownian motion increment from T2 to T1 and the Brownian motion increment from T2 prime to T1 prime these are independent as long as these time spans are independent. Now, if they overlapped, let's say T1 came over here and was less than T2, then they're no longer independent. But as long as these time increments are independent, or excuse me, these time spans don't overlap, then these increments are independent of each other. So one thing that implies, if we take both these properties together, these properties imply that if we took a Brownian if we took samples of the Brownian motion at regular intervals, the increments would be IID. To see that, let's sample our Brownian motion at integer time instance. So the increment here is B1 minus B0. The increment here is B2 minus B1, so on. Actually, let me keep writing some of those. Increment here, B3 minus B2. Increment here, B4 minus B3. So you'll get the idea pretty quick, I think. So if we look here by my property on the last page, the increment is the normal distribution with mean 0 and variance sigma squared times the difference in times. So 1 minus 0 is 1. So I get normal 0 sigma squared. This is distributed again. The difference between 2 and 1 is 1. So that's normal 0 sigma squared and so on. And by the second property, the increments are independent. So that leads to something interesting, which is what I'm going to call the Markov property. Brownian motion. So if you know a sequence of Brownian motions, or excuse me, of points of Brownian motion, it's called T1, T2, T3, and so on. We call this Tn. So in other words, you have a Brownian motion and you sample it at many points. They don't have to be regular, just as long as they're different. And without loss of generality, we're going to say T1 is less than T2 is less than T3, and so on up to Tn. You might think, okay, gee, we know all these points of the Brownian motion, and what I want to know now is, given all of the evidence of the past, actually it will be convenient for me to include Tn-1 here. Given all the evidence I have of where this Brownian motion came from, what can I say about the last points? In other words, I'm looking for the probability, or the probability density function rather, of B at Tn. So this is what I'm interested in, given all the points in the past. So B Tn-1, and so on down to BT2, BT1. So in order to get this, what we need to know, we already know by assumption here, B of Tn-1. But from that, how do we get Btn? Well, I mean, trivially, we can write B of Tn is equal to B of Tn minus B of Tn-1 plus B of Tn-1. So I mean, on the right-hand side, I just subtracted and added by B of Tn-1. But writing this a different way, that is the increment from Tn-1 to Tn. And that, by the second property, is independent of any past interval. So in other words, if you look up here, all these time units are in the past. Let me just add this here. None of these time instants will overlap with this interval between Tn-1 and Tn. So these will all be independent of everything that happened before. So if I know what B of Tn-1 is, as I do here, none of the other stuff matters. So from this argument, we can say f of B Tn given B Tn-1 and so on down to BT1 is equal to f of B Tn given B Tn-1. This implies the Brownian motion is a Markov process. In other words, it only depends on the past through the present, or the future only depends on the past through the present. And I can know everything about what happened to this Brownian motion before now, and it doesn't matter because the next increment is independent. And that's basically a Markov chain. That's great because that simplifies the analysis kind of a lot. And it also makes these processes relatively easy to simulate. I'm just going to make one mark and then we'll talk a little more about simulation. So we can talk about Brownian motion with drift. So it's still a Wiener process, but it's a Wiener process with drift. And basically what happens is everything is the same. It's still Markov. But the increments are distributed as follows. Now, if you think about it, what we had before, I'm going to write what we had before, and then I'm going to erase it. So just fair warning. This is distributed. This is what we had before. It was mean 0 and variance sigma squared T2 minus T1. Now, if you think about what drift means, that means every time as time moves on, there's a certain deterministic component. So in other words, if this is a Brownian motion, imagine the mouse cursor as a random Brownian motion. A Brownian motion with drift will have some bias to it. As you can see, in my second example, the mouse cursor, the pointer cursor was moving randomly but biased in a certain direction. And that'll show up in the mean here. So what's going to happen is that if you have drift with velocity v, then on average, the center of the distribution, if you like, is going to move by v times t2 minus t1 every time instant. So that's the distance. This becomes the distance of the drift, the average distance traveled by the drift over this time interval, and that's going to show up here. So let me erase that and correct it. So everything's the same. It's still Markov, except b t2 minus t1 is now distributed with a mean, with a shifting mean. So drift implies a shifting mean. Another fun thing about the Wiener process, whether with drift or without drift, is that it's relatively easy to simulate. And the Markov property makes the Wiener process easy to simulate. So again, you can pick whatever time base you want, but if we just go with an integer time base and we want to generate B0, or we want to simulate B0, B1, B2, and so on, remember our argument going from here to here, it's just a Gaussian random variable with mean 0 and variance sigma squared. Going from here to here, it's a Gaussian random variable with mean 0, variance sigma squared, and so on. So basically, each time instant, you can add the increment. If you have drift, so this is without drift. If you have drift, of course, the increment is just given by V. In this instance, it's V T2 minus T1, but T2 minus T1 is 1. So in this instance, it would be N V sigma squared. This is with drift. If you want an arbitrary, time increment, so for instance, B of 0, B of delta T, or an arbitrary sampling interval, 2 delta T, and so on, the increments now become, if you go back, you can see this, but we scale the increments variance and mean by delta T. So this would be V delta T, sigma squared delta T. I am going to upload, along with these notes, I'm going to upload Jupyter Notebook. Containing sample simulations. If you don't run Jupyter Notebook, that's fine. You can instead do this on Google Colab, which is free. Just write that here. I'm sure many of you are familiar with Google Colab already, but basically what you do is you just upload, the notebook that I have that I'm putting with these notes, and you can simply run it in Google's environment. And you're running it on Google servers with all the right packages, so it should be straightforward. Okay, so now we can model the Brownian motion of an individual molecule. Let me just add one more point here. We need to specify sigma squared. So what is sigma squared? So for a one-dimensional Brownian motion, sigma squared is actually equal to 2 times d. Okay, so this is, let me be a little more clear here. For a one-dimensional Brownian motion, sigma squared is 2 times d, where d is the diffusion coefficient. The diffusion coefficient has to do with both the medium, in other words, the medium that the particle is propagating through, and the properties of the molecule that's propagating itself. There's actually a formula for this. It is D equals KBT divided by 6 pi eta RH, where KB is Boltzmann's constant. T is the temperature. Eta is the viscosity. And RH is the hydraulic radius. Viscosity of the medium. And RH is the hydraulic radius of the particle. So as you can see, D is dependent on both the medium and the particle. And if for biomolecules, D will be, this is an extremely rough guideline and this will not always be followed, but it should probably be in the range of 1 to 10. And it's the units here would be micrometers squared per second.